Hello, Astronomy. Mr. Janowski here. This is part 7 of the chapter 13 slides. In the last part, we learned a little bit more about how we use the spectrum or the spectra of different stars to determine different things about them, and in particular, using the Doppler shift to notice things about their motion. And in this part, we're going to learn about binary stars and why binary stars are so important. So let's get started. So, when is a star's light blue shifted? Are you blue shifted when when the star is moving towards us or moving away from us? You're blue shifted when the star is moving towards us. And you are red shifted when the star is moving away from us. So yeah, you look at the spectrum you're getting from the star, you look at the spectral lines, and you look for the certain patterns, and you try to see, are those patterns a little bit towards the blue, or are they a little bit towards the red? And by measuring how much they're shifted one way or the other, you can figure out how much the star is moving towards us. So keep this in mind. This will be important in this part of the slides. So yeah, binary stars. These are stars that orbit each other, held together by gravitational attraction. So they are most often pairs, meaning just binaries of just two stars, but you can have trinary stars, triples, quaternary stars, quadruples, quintuples, and we know of at least one sextuple, where you have six stars that are all, in some sense, gravitationally bound to each other. So if you're saying binary, you're either meaning binary either means that there are two. It's also kind of the more general name for the class of there's several stars bound together. So yeah, usually pairs, but you can have more. So are stars, how often are binaries? It depends on the size of the stars. So the hottest stars, these are also the biggest stars, it'll turn out. Most of them, about 80% of them, do have a companion. About half the stars that are like the sun, which are called G-type stars, have companions. The sun, it turns out, does not. It's 50-50. It turns out the sun didn't have a star, didn't have a companion star. And the cool dim stars, which tend to be the really tiny ones, most of those lack companion stars. So yeah, they're kind of common depending on the size of the star. So the most important thing about binaries is that they give us a way to measure a star's mass. So the star's mass is going to determine the force of gravitational attraction. So this is a formula we had from earlier. I think this was from chapter 3 or possibly, yeah, this was chapter 3, Newton's laws. So the masses of the stars will determine the strength of the gravitational force. And that gravitational force will determine how long it takes the stars to orbit each other. So by looking at their orbital motion, you can figure out the stars' masses. And the masses are important because the masses of the stars will determine how long that star will live and how that star's structure will change as it ages. So yeah, the mass is very important. And binaries give us a way to measure the mass. So typically binaries are a few AU apart, AU being the astronomical unit, so the distance from the Earth to the Sun is 1 AU. Most binaries are going to be a few AUs apart. So different theories about how these things form. So when you have stars that are a few AU apart, it may be that they formed, they became a binary where one of them captured the other one with its gravity as the other star was just passing by. But you also have stars that are called contact binaries. So these are binaries that are so close that they actually touch, which means that each star's cloud of gas is actually combining with the other ones. So when we have contact binaries, we think that these probably formed at the same time from the same parent cloud of gas. But instead of that cloud of gas collapsing and forming one star, it formed kind of two clumps near each other that each one of those became stars, and they're very close together. So different ideas about how these things actually formed, but this is, kind of the most commonly accepted one. So Mizar and Alcor. So these are famous stars in the handle of the Big Dipper. So a little bit of useful astronomy. Here in the Northern Hemisphere, we can see the Big Dipper on any clear night, at least where we live in Pennsylvania. So if you're looking at the Big Dipper, if you look at the stars that make the front of the bowl and you draw a line from them, they will point towards Polaris, the North Star. So this is an easy way of figuring out which way is north at night. If you can see the Big Dipper, find the front of the bowl part of the dipper, or the bowl of the ladle. Draw a line between them. That'll point to a Polaris, and that's how you know what is north. But that's not what we're talking about here. Here we're talking about Mizar and Alcor. So if you look at the handle of the Big Dipper, there's a kink in the handle, and that kink, which looks like one star, depending on the quality of your eyesight, is actually several stars, and they're called Mizar and Alcor. So by themselves, Mizar and Alcor are not binaries. Turns out that each one of them is of themselves a binary. So yeah, if you look at them just quickly or with poor, typical human eyesight, you're going to think this is one star. If you have better eyesight, you're going to think this is two stars. If you have a good telescope, you're going to see, well, there's actually a lot more going on. The one star that we call Alcor is actually two stars. So Alcor is of itself a binary. And the other thing that we call Mizar, which we think, if you have good eyesight, you'll think, oh, that's a separate star of itself. It's actually a pair of binaries. So Mizar is actually four stars. So we call these stars visual binaries because if you have a telescope, you can actually see them as separate, and you can see them going around each other with a decent telescope. So these are the first class of binaries. Contacts would be the first. These are visual binaries because, you can look at them with a telescope, months or years apart and actually see their motion. So other times you're going to have binary stars that are so close together that even with a very good telescope, you can't see that they're separate. So how do we know that they're binaries? What gives us the right to call them binaries? Well, these are what we call spectroscopic binaries. So you can look at a star, and even if you can't resolve that is actually two separate stars, you can look at the light of the star. And instead of seeing one set of spectroscopic lines where you expect to see them, you'll see separated ones, which means one is a little bit red shifted, one is a little bit blue shifted. So instead of seeing one line, you see this double set of lines. And this tells you that these are binary. Because if one of these stars in the binary happens to be moving a little bit towards you, that one's light is going to be a little bit blue shifted. If the other one at that time happens to be moving a little bit away from you, well, that one is red shifted. So the lines separate. And this is how you can tell, just by looking at the spectra, that you have separate stars. Even if with your best telescope, you can't actually see the separate stars or see that they're separate, you can still tell by their motion and by their spectrum that they are actually separate. So if you watch a star over its full cycle of motion, so if it's visual stars, you're looking at them over years and comparing photographs and doing things like that. Or if they're spectroscopic stars, you're watching how these lines move closer and away from each other. You can figure out the speed of each star's motion, the period, which is just how long it takes for them to go through one complete cycle of orbiting each other. Sorry, I thought I had muted my phone. I had not. So by using this information, you can figure out the mass of the stars. So here is a very good crash course astronomy on binary stars, goes over the different types that we're going to talk about, and has some nice, useful animations that can explain things a little bit better than perhaps you can from listening to, or better than I can. Let me take that over. It's got nice animations Dr. Plate is using that explains these things perhaps better than I can because I don't have the same animations available to me right here. So yeah, watch the Crash Course Astronomy. I'll put a link to that in the description, and I'll put a link to the Kahoot as well. So in some very rare cases, you'll have binary stars going around each other, and their orbits will just exactly line up so that we're looking at them kind of edge on. So when that happens, we're going to actually see one star pass in front of the other, and these are called eclipsing binaries because at different times in their orbit, one star will appear to eclipse the other. So these are kind of extra useful. They're rare, but when these happen, we can actually get a little bit of extra information out of them. So by actually measuring, these little times right here, where one star starts to eclipse the other, and we see how long it takes for them to eclipse, and then later that part will get undone, like over here where it's changing. You can actually figure out the radii of the different stars. So here's this image, slightly bigger. So again, the most important thing about binaries is it gives us kind of a useful way to measure their masses. So you don't really need to know all this, but this is kind of a modified version of Kepler's law. Actually, a modified version of Newton's version of Kepler's third law of orbital motion, whereby measuring the semi-major axis, so how far apart the stars are in their orbit, and the period, which is how long it takes them to complete an orbit of each other, you can figure out the combined masses of both stars together with this formula. And then by other ways, you can figure out the masses of the stars individually. So here's a couple slides where you would figure out the math. We'll go through this quick. So two stars orbit each other with a period of 10 years and a semi-major axis of 6 AU. So what is their combined mass? So you would want to figure out, well, 10 years, which piece of information is that? And 6 AU, which piece of information is that? The 10 years is the period, and the 6 AU is the semi-major axis. So that's the A in this formula. So plug those numbers in, do the math. Turns out that the combined mass of these stars is about 2.16 times the mass of the sun. So there's other ways to figure out the individual masses of the stars, but this formula is a good way to get the combined masses, what both stars together weigh, what their mass is. So now if we look at Alpha Centauri A and B, so these guys are back, they're from the beginning of the chapter. They take longer to orbit, about 68 years. And they have a semi-major axis of 20.6 astronomical units. So what is their combined mass? So plug these numbers in, and you get a combined mass for these two guys of 1.89 times the mass of the sun. So yeah, sometimes stars take years to orbit each other if they're in binaries. Sometimes they take months. Sometimes they take days. In that video, the Crash Course Astronomy one, he'll tell you of a particular star, a very weird combination of I think it's a neutron star and a white dwarf that actually orbit each other every 11 minutes, which is just kind of crazy. These two massive things flying around each other that quickly. So yeah, we can now measure the masses of stars using binaries. There are other ways, again, as I keep saying, that you can determine the individual masses of the stars. So through this kind of measurement, we determine that most stars have a fairly narrow range of masses. Most stars are going to be between 0.1 times the mass of the sun and about 30 times the mass of the sun. So that may not seem like a small range, but it is. You know, you're within an order of magnitude of the sun either way. Order of magnitude means, yeah, your lightest ones are about 1/10. If it's an order of magnitude means factor of 10. So your least massive stars are about 1/10 times the mass of the sun. And your most massive stars, they're still in order of magnitude. They're about 30. So a little more than 10 times the mass of the sun. There are exceptions. There are a few stars that weigh, hundreds of times the mass of the sun, but those are very rare. Most stars are within a factor of 10 in order of magnitude, the mass of the sun. And our sun's right about in the middle, of course. So a quick review. Why are binary stars so important? They're so important because they give us a way to determine the masses of the stars. So that's very useful. So what do we call binary stars that are so close together that they actually touch? Those stars are called contact binaries. So yeah, if they're so close together they actually touch, you won't see the separate stars, so it won't be two separate spheres. They'll actually kind of join together, kind of like a peanut shape here. And more than that, the gravity between them will kind of deform them. So neither one of these stars is particularly round, sphere-like. They kind of take on this shape. So what do we call binaries whose orbital motion around each other can be seen by comparing images taken a few years apart? These are what we call visual binaries. So Mizar and Alcor are visual binaries, although, again, it's actually more complicated than that because Alcor is of itself a visual binary and Mizar is a pair of visual binaries. But the idea here with visual binaries is you can actually take images that show the stars as separate. And if you take images over the course of several years, you will see the stars' positions changing, and you can measure their orbits that way. So not all binaries are visual. Some of them are so close together that you can only measure them a different way. So what do you call the binaries whose orbital motion can be seen only by their spectra? These are the spectroscopic binaries. So again, in the case of spectroscopic binaries, you get pairs of lines. So at any given point, one of the stars will be moving towards you, and that star's lines will be a little bit blue shifted, while the other one's moving away, so that star's lines will be a little bit red shifted. So you'll keep getting these pairs, and by watching how these pairs of lines change over time, you can determine how long it's taking these stars to orbit. And then what do we call the binaries whose orbital plane is such that one star seems to pass in front of the other when we're looking at it from here on Earth? These are called the eclipsing binaries. So yeah, the stars have to be orbiting in such a way that their orbital plane, the flat plane that they're orbiting each other in, happens to be lined up exactly so that we're looking at it edge on from Earth. Otherwise, they're not going to seem to eclipse each other. So that makes these stars fairly rare. But when it happens, you get extra information. When you have eclipsing binaries, there's a clever way you can use to determine the actual radii of the different stars. So we have other ways of calculating the radii, but it's nice to have this way too to confirm, the accuracy of the other way of measuring these. So that's it for this part of the slides. Hopefully you found that interesting.